Hello guys, in the previous video we had seen that sound can be considered a wave. Now let us see some characteristics of a sound wave. A sound wave can be described by its frequency, its amplitude and speed. One by one we will see what is frequency of a sound wave, what is amplitude of a sound wave and what is speed of a sound wave. Sound wave propagates in a medium through alternate regions of compression and rarefaction. These are nothing but density variations in the particles that are present in the medium. In the first picture here we can see that the particles which are present near to the speaker are in a compression region. The next region is the rarefaction region, and alternatively this kind of compression regions and rarefaction regions propagate through the medium till it reaches to the listener. Now this density variation can be correlated to the pressure variation in the medium. High density regions correspond to high pressure regions. The region of compression which has large number of particles, thereby increasing the density of the region, is also a high pressure region, because as the density is more, which implies pressure is also more. Similarly, the rarefaction region has particles which are less in number. Therefore, the density in this region is less compared to the compression region. Hence, the pressure of this region, the rarefaction region, is also less. Now we can relate density or pressure with distance as the sound wave propagates. Near to the speaker, we have a compression region. Therefore, the density or pressure is high in that region. Now as we move on to the rarefaction region, the density or pressure reduces below the average density or pressure. Now similarly, this thing continues alternatively. Hence, these variation in density and pressure would help us to relate the frequency, amplitude and speed of sound wave. Let's move forward. What is frequency and time period? The frequency and time period of a sound wave is related by the formula nu equal to 1 upon t. Suppose the time period of the sound wave is t seconds. Therefore, the frequency will be 1 upon t seconds. Now we will see some terms that are used in context with the sound wave. The first term is pitch of the wave. Pitch is how the brain interprets the frequency of an emitted sound. The faster the vibration of the source, the higher is the frequency and the higher is the pitch. A high-pitched sound corresponds to more number of compressions and rarefactions passing a fixed point per unit time. The figure here shows a wave disturbance. The first figure corresponds to a wave which has low frequency, which means it is a low-pitched sound. The second wave corresponds to a high frequency wave, which means it is high-pitched sound. And why is it so? Because we can clearly see that a more number of compression and rarefaction regions pass through a fixed point in the second wave, whereas in the first wave, the number of compression and rarefaction regions passing through a fixed point is less compared to the second one. The second term that we need to know is the amplitude of the wave. The magnitude of the maximum disturbance in the medium on either side of the mean value is called the amplitude of the wave. Amplitude is denoted by the letter capital A. Amplitude determines the loudness or softness of the sound. The amplitude of the sound wave depends upon the force with which an object is made to vibrate. Loud sound can travel a larger distance as it is associated with higher energy. A sound wave spreads out from its source. As it moves away from the source, its amplitude as well as its loudness decreases. The figure here shows two wave disturbance. The first one corresponds to an amplitude which is less, and the second one corresponds to an amplitude which is high. Less amplitude corresponds to a soft sound and high amplitude corresponds to a louder sound. Amplitude is the maximum disturbance from the mean value on either side of the wave disturbance. Therefore, this quantity is A. Similarly, this is also A. In the second figure, this A is larger. Now let's move on to the term timbre. The quality or the timbre of sound is that characteristic which enables us to distinguish one sound from another having the same pitch and loudness. The sound which is more pleasant is said to be of rich quality. Tone. A sound with single frequency is called a tone. Note. A sound with many frequencies is called a note. The speed of sound is defined as the distance which a point on a wave, such as a compression or a rarefaction, travels per unit time. We know speed is distance divided by time, and distance here is nothing but the wavelength of the sound wave. Therefore, speed is wavelength upon the time period of the sound wave. Now, what is wavelength? Wavelength is one complete cycle of sound wave. So in this, I have drawn two wavelengths. The first one is from point A to point B, and the second is from point B to point C. So AB corresponds to 1 lambda or 1 wavelength, which is also equal to BC. Now we will look into a problem and see how do we calculate the speed of sound and the distance it travels correspondingly. A sound wave has a frequency of 2 kHz and a wavelength of 35 centimeters. We have been asked to calculate the time it will take to travel 1.5 kilometers. So first, in order to calculate the time taken, we need to find the speed of the sound. And to find the speed of the sound, you have to calculate its wavelength and time period. In this question, the wavelength is given to be 35 centimeters. And from frequency, we will calculate our time period. So time period is nothing but 1 upon frequency, which is 1 upon 2 into 10 raised to the power of minus 3 seconds, because this is kilohertz. This is nothing but 0.5 into 10 raised to the power of minus 3 seconds. Now, we have been given the wavelength, so therefore speed V is wavelength upon time, which is 35 centimeters divided by 0.5 into 10 raised to the power of minus 3 seconds. Now I convert the centimeters into meters by multiplying it by 10 raised to the power of minus 2 meters. So this becomes 3500 divided by 5, which is 700 meters per second. Now to calculate the time it takes to travel 1.5 kilometers, we can find it by time taken is distance divided by speed, which is 1.5 into 10 raised to the power of 3 meters divided by 700 meters per second. This comes out to be 1.5 divided by 7 into 10 seconds, which is nothing but 15 upon 7 seconds, which is 2.1 seconds. Moving forward, now we will see what is intensity and loudness of a sound. The intensity is the amount of sound energy passing each second through a unit area. Similarly, loudness is the measure of the response of ear to the sound. One thing to be noted here is loudness and intensity are not the same, though they are unknowingly interchangeably used in our day-to-day life. Now let's see speed of sound in different media. Sound travels in different mediums with different speeds. Its speed is maximum in solids. Example, when a train is about to arrive at a station, you can hear the sound that it makes from the railway tracks that is just in front of you. This is because sound travels faster in the tracks which is solid compared to that in air. Now when the speed of sound is compared to that of light, the sound speed is very less compared to that of speed of light. Speed of light is approximately 3 into 10 raised to the power of 8 meters per second, while that of sound is approximately 340 meters per second in air. This is also evident from the fact that we can see lightning much before we can hear the thunderstorm. With this, we come to an end on the second video of the chapter Sound. In the next video, we will learn about sonic boom, the structure of human ears, and end the chapter. Thank you.